welcome to the podcast. This is Mr. White.
And Mr. Sadler.
And today we're going to talk about Newton's third law. Some people would say that this is Newton's final law, but that would be incorrect. We don't call it the fourth law. We call it Newton's universal law of gravitation, which discusses how the moon interacts with the Earth with the sun with the Milky Way, etc.
About gravity.
About big gravity, not the little things that we're studying in class, the smaller Earth things that we deal with in class. So Newton's third law, and this is one that everybody knows, actually. It's not too complicated at all. For every action, there is an equal but opposite reaction. And I suppose maybe we should do a little better. We should probably say for every action force, there is an equal but opposite. There is an equal. Forgot the word opposite. But opposite reaction force.
So this is really stating that just forces come in pairs.
Yeah, and that's a really important thing to think about. So I'm sitting in this chair right now. Obviously, the weight of me is pushing down on the chair, and the chair and I are pushing down on the floor. Well, if the floor didn't provide a force up, then we would fall through the floor.
Right.
And if the chair didn't supply a big enough force up, then the chair would collapse under my weight.
Right.
So that's all that that's saying. I actually like the mathematical version of this, which states that F1 is equal to negative F2. Equal, but opposite.
So the force up is equal to the force down,
Correct.
or the force right is equal to the force left.
And this applies to all kinds of things. So I started with this chair analogy. So if I've got a chair here and I'm sitting on the chair, okay, what we have going on here is that my weight, I'm going to draw this off to the side, my weight is pushing straight down. So my force due to gravity, and I will often write it as Fg. And the chair is supplying an up force, so F sub chair, just so we're descriptive. What do you notice about these two arrows, Mr. Sadler?
They have to be equal.
They have to be equal in length, and they're pointing in
Opposite directions.
So it goes back to our whole equal but opposite thing. Okay, so that's one way with which we can state this for any stationary object. And I believe in today's investigation, we spanned a meter stick, and we put some weight on it, and we watched the meter stick bend. And obviously, the meter stick held the weight, because if it hadn't, what would happen to the meter stick? It would
bend.
It would bend and then eventually
break.
And so that would cause us some problems. So if the chair here couldn't help us out, then we would fall through the chair.
Well, and the chair does probably bend a little bit when you sit down. Notices the force.
But you don't notice it just with your eyes.
Right.
You can pick it up with a camera. There's some other ways in which you could do this. The other situation, which is a lot less obvious, is, so this is what we would call a static situation. Okay, would be the dynamic situation. So I've got a car, another one of my classic drawings, more bus-like, but okay. I've got a car, it's traveling down the road, okay, and there's all kinds of things happening here. Okay, first of all, does my car have weight?
Of course.
Yeah, and that's pushing straight down. Okay, and does the road push back up on the car?
Of course, otherwise it would be sinking into the ground.
And so these are clearly equal but opposite because there's no change in the vertical motion
Right.
here. And so what we call this is Fn, which is sometimes called the normal force. Now I've seen textbooks just go ahead and call this capital N. I don't like that because the unit for force is newtons, which is also capital N. I think that's confusing. Now I'm going to say dynamic, and I'm going to say constant motion. So we've talked about this situation before, the cruise control on your car,
Right.
where the engine would be supplying a forward force per Newton's third law that would be equal but opposite to
the force of friction.
The force of friction.
Air resistance or whatever.
Now, friction can come in a lot of forms. It can come tire to road. It can be due to air.
Could even be due to the engine.
It could be, yeah. There's a lot of factors of friction. Now, the symbol for friction is lowercase f. We actually talk about friction in Section 7. Something called the mu of the shoe. Classic physics experiment, of course. So this is a dynamic situation where forces left to right are equal but opposite, and forces up and down are equal but opposite. But what you would notice, if we go back to our second law stuff, that the sum of the forces in the y direction is equal to 0, because the acceleration is 0 vertically.
Right.
And the sum of the forces in the x direction is also 0, because we have constant motion, so 0 acceleration. And as a result, there are forces, but when you add them together, they cancel each other out.
And it looks like to me that forces sometimes cause no movement, and forces sometimes do cause a movement.
Right, forces cause a change in motion. So like if we were to let off the gas, all right, so then we move away from the third law and we go back to the second law. So if we're back to our car/bus here, okay, if I were to let off the gas, let's say I put the car in neutral, the bus still has weight, the earth is still pushing back, providing a normal force, but now friction is winning because I've killed the engine. And as a result, now the sum of the forces in the x direction is equal to negative ma, because I have a negative acceleration caused by the frictional force. So the only force you would talk about here, and this is getting a little math heavy, but would be friction, and this is this is one way with which we could calculate it. The other scenario would be if we wanted to accelerate the bus or my car, okay, first of all, you can't do anything about friction. It's always going to be present, just like gravity. So friction is friction, but if I wanted to accelerate the bus forward, then my engine force would have to be bigger, and so the sum of the forces in the x direction would be positive ma, or F engine of bus minus friction, and then that becomes a mess. But writing down the equations isn't terrible because you just pull them from your picture. Hey, what are these pictures called?
Free body diagrams.
Yeah, free body diagrams. I like free body diagrams because you don't have to be an artist to do this at all. What I end up doing is, I drew the guy in the chair and I drew the bus, but essentially everything becomes a dot. So this doesn't matter. This could be the planet Earth. This could be a mosquito. It doesn't matter. Because what we're assuming is that all of the mass is concentrated at the center of the object. And then we draw the forces here in any which way they might exist. So let's see. How about this computer sitting on this table here? Okay, the computer has some weight directed down. The table is pushing back up with this contact normal force, and I'm not pushing on it sideways or anything like that. So that would be my free body diagram. If I were to give it a push, and assuming the computer doesn't move, okay, even if it did, I would be supplying a pushing force, which of course would be dealt with by friction.
I think that's the point that I was trying to make, is the forces don't always cause things to move.
Right.
I mean, this computer sitting on the table, just because there's a force down and a force up, it's not moving.
It can be a static situation, but we can have many forces acting on it.
Right.
Buildings constantly undergo this.
Right.
Right. We're very thankful our buildings are static.
Right.
Right, because they have forces balancing each other out in all possible directions. They're not falling down. They're not rotating. They're just sitting there.
The students in the Investigate today, when they were pushing against the wall, they assumed that the wall didn't push back. But if the wall didn't push back, then you couldn't have went across the floor.
There would be nothing to supply a backward force.
Right.
That's correct. So, that's the third law. We're very well aware of this. If so, one example I like to think of, I was once young and a little irrational from time to time. All right? So the third law, again, what is it? For every force,
There's an equal and opposite force.
there is an equal but opposite force.
So you punched a brick wall or something.
Sure.
All right.
Right. So let's say I'm not quite that dumb. I can remember once getting into a scuffle with another young lad, and we took it upon ourselves to settle our differences by punching each other. And he punched me, and I punched him, and 2 or 3 times in, my head hurt because I had been punched in the face a few times, but I also noticed for some reason my hand hurt as well. And so if you supply a punching force, okay, against the side of someone's face, all right, and look at that, look at those art skills, Mr. Sadler.
Force on face equals force on hand.
Yeah. So I am supplying a force to the right, but his face is supplying an equal force back to my hand, which is not something that I was really looking for at the moment. And so that fight didn't go on too much longer because I realized that that hurt, right? There's all kinds of examples of this in the world of football. They always talk about the big hit the quarterback takes. Well, the defensive player, according to the third law,
Right.
takes the same hit.
Exactly.
Now, the one major difference is sometimes the quarterback or running back doesn't see it coming. They can't brace themselves for it. The defensive player always knows when he's about to tackle somebody. But defensive players get concussions too. Boxers get concussions. They have broken hands because of punching, etc. So this third law thing, it applies everywhere.
I think the only way that you help yourself out is if you have more mass. Maybe you can hit a smaller guy, but the force is equal. But
and so why don't we have that discussion about the bug windshield?
okay.
Okay, that's a good point, Mr. Sadler. So let's see. Let's just draw a bigger car here. I know, not much of a car. Okay, so here's my car, and here's my Mosquito. Okay,
Right.
and the car is going fast, and the Mosquito is going. And what's going to happen to the Mosquito in the car?
They're going to hit one another.
They're going to hit one another. So eventually, my Mosquito here, he's going to be on the windshield of the car. Is that correct? So the question is, which experiences a
More
larger force?
And we just said that the forces have to be equal.
Right. And so the answer to the question is neither. They both experience the same. Now you can say which has a bigger acceleration. And because of Newton's second law, which is F equals ma, if the car, okay, so let's go Mosquito small mass, okay, and my car has a big mass.
Right.
If they both experience the same force, what can you tell me about the acceleration of the car? It has to be
A lot less.
real tiny.
Yeah, tiny.
And the acceleration on my bug, because of its tiny mass, must be really
Big.
big. Right?
Right.
So this helps clear up some other things. So if you were to punch a smaller guy, if Mike Tyson were to punch me in the face, seeing that he weighs over 200 pounds, that ends poorly for me because I'm not even close to that, and he actually knows how to punch another human being.
Right.
His larger mass is going to distribute a larger acceleration over my smaller mass. His fist will experience the same force as my face. I will be in the hospital. He will be sleeping comfortably in his mansion.
Right.
Right. So we start to see how some of all of this works out. So with that said, I believe that covers the third law
Yep.
pretty well. So signing off, this is Mr. White.
And Mr. Sedler.